Hello everybody. This is Urian from Power Electrical Developing Advanced Research Group PEDAR. I'm so happy to have you here. And I hope everything goes well for you. In this training video, I'm going to talk about simulation of the paper entitled Decentralized Multi-Objective Energy Management with Dynamic Power Electronic Converters and Demand Response Constraints prior to commencing the simulation outlined in the paper. Let's review the problem formulation in this paper. Actually, in this paper, the authors respond to this main question. The question is here: where is the best location and where is the best phase and how much is the best generation for each type of distributed generation in a three-phase and balanced power distribution network, with aim of minimizing the objective function, which consists of the objectives of losses, voltage deviation, and operation cost. So if you look at the main objective function in this paper, which is defined by Equation 25, the objective function consists from F1, F2, and F3, where the F1 is losses, F2 is voltage deviation, and F3 is the operation cost for each type of the DGes. Also, this paper asks different types of distributed generation such as PV, wind turbine, microturbine, and diesel generator, and BESS and energy storage. So let's go to run simulation of this paper to see the simulation results. In order to run the simulation file, you should open this Matlab simulation file and copy this link address from your computer and paste it in your link address of the Matlab software. And press the Enter key to see the simulation file. In order to run the simulation file of this paper, you should open the main.m file and see the Matlab code for simulation of this paper. There are many different parts for simulation of the paper, but the most important challenge in simulation of the paper is related to the solving three-phase and balanced power flow in distribution power network. In this regard, the paper pays to dynamic energy management. For 24 hours of a day, at the first step, you need to enter input data. Such as network data from the Excel file that is named feeder IE10_sin regulador. Okay, so the load feeder function calls this file, where this function is located in your simulation folder. If you open this file, you can see the information data for a three-phase and balanced power distribution network. This sheet shows you the general information about this case study. Also topology of the network, configuration of the network, and imbalanced load which is saddled at each phase in the network, and the other information data. Also, three-phase load flow is used to solve the power flow in three-phase and balanced power network. After that, at the first step, the compiler starts to calculate each terms of the total objective function without considering the dynamic energy management. After that, the optimization algorithm is called using this variable function, which is located here. To perform the dynamic energy management and determine the best node, best phase, and best generation of DGes. Okay. If you want to run simulation and see the simulation results as online, you can press the run key and waiting for finishing the simulation and printing. The output results, but in this path, you need a lot of time for finishing this simulation. On the other hand, if you want to see the simulation results using the saved data for previous simulation run, you can open the fast result file and run it. This M file uses the simulation result that is saved in the Optim data file. So you can run this file and see the simulation result immediately after. Pressing this key. If you press this key, you can see the optimal solution for each hours of a day, the 2 for each scope and the 3 for each amount of a day. Where the best location phase is determined by number 4 for phase O, number 6 for phase B, and number 8 for phase C. These numbers are considered for different type of phase. And also, this figure shows the best bus location, and this figure shows the best generation for each time of a day. Also, you can see these results for another type of the distributed generations. For example, in demand response curve, this figure shows the power which is need to be reduction by demand response program for each time of a day. It's about blah 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 kilowatt at each time of a day at each bus of the network. and at each bus of the network. Also at each phase of the network. Whereas the number chart is named for bus, for phase A, for phase B, and for phase C. Also, you can see the base generation of microturbine at each time of the day, at each bus of the network, and each phase of the network. Also, you can see these results for diesel generator, and microturbine, wind turbine, and PV system. And you can see the voltage deviation after dynamic energy management and before dynamic energy management, and active losses after and before dynamic energy management. Also, you can see the situation of energy storage at each time of a day. You can see minus power, and you can see plus power at peak of load. Where the battery is started to charge, and where is start the discharge. And you can see the before generation, demand response, and after each demand response, distribution generation. Many thanks for your attention. And I hope see you later again. Thanks.